My name is Joel Thompson. I work at Bridgewater Associates. So just to give you a little bit of introduction about me, I'm a Vault enthusiast and community member. Earlier this year, I wrote the Am Auth method of Vault's AWS Authentication Backend. If you remember when it went from AWS EC2 to just AWS, I was the person who wrote that code. And I've spent the last 9 years at Bridgewater in a bunch of different roles spanning development, operations, security. So I've had my fingers in a lot of the pies. Well, I've mentioned Bridgewater a few times. So who is Bridgewater? I think it's really well put by Brian Kreider, who's the head of our client services and marketing department. He said that from a values perspective, we are trying to understand the way the world works. That's what our business is. And so we're really interested in people that have a sort of deep curiosity, people that have the patience to understand deep and complex systems. Whether those are biological systems or economic systems or political systems, it doesn't really matter. And in particular, we try to understand timeless and universal, fundamental and systematic principles that drive the world's economies. What do I mean by this? When I say timeless, we're not just looking at what's going on in the US economy today, and not just in the dot-com boom or the dot-com bust or the Great Depression or the Great Recession, but really across all time. And we're looking for not just the US, but universal, what drives the world's economies all over the world. Then when I talk about fundamental, what we search for is cause and effect relationship, to try and reason about the cause and effect relationships that lead to the economic changes that we observe. So we're not just observing correlations and trading on those. And then we want to make our understanding systematic. We take logic and we encode it in software so that when we have an idea, we can repeatedly trade on that same idea over and over again. And if it doesn't make money, we can stop doing the things that aren't making money. And over time, we build a compounded understanding of what drives the world's economies. And then we take that understanding and we manage... So we take that understanding, and we manage about $160 billion for institutional investors all over the globe. And when I say institutional investors, that's important. Our clients aren't high net worth individuals. They aren't rich people who want to get more money. Our clients are institutions like public school teacher pension funds. These are the people who depend upon us to remain secure and to have an income in their retirement. So why is Bridgewater here? Well, $160 billion is a big target that a lot of bad guys are going to want to steal from. And we care very, very deeply about protecting our clients. That $160 billion isn't our money, it's our clients' money, and we have an obligation to do everything we can to protect it. And we are a massively technology-enabled company. When I said we're systematic, we cannot be systematic and compound our understanding of what drives the world's economies without a lot of technology in order to encode our understanding and make the same sorts of decisions day after day. And over the last several years, we've been placing a very large bet on AWS in order to improve our technology agility, as well as keep up with the evolving security threat landscape that exists out in the rest of the industry. But as we started going into our cloud journey, we ran into a pretty fundamental security challenge, and I'll talk about that in a second. The problem is, I call it often, is the autoscaling group problem, which is that these are awesome, right? You let Amazon give you more capacity when you need it. But there's a big question, which is, how do these instances get things like their database passwords? The Vault team calls this the secure introduction problem. Now, Vault is awesome, right? And so the answer could very well be, use Vault. But then if you just say use Vault, that introduces an equivalent problem. How do you get a Vault token onto the instance that's using it? And over time, I sort of became convinced that there weren't any good solutions, only awkward workarounds. And then as Amazon's expanded their services to include things like ECS and Lambda, it's even more important of a problem to solve so that we can take advantage of these great new services that cloud providers are offering and integrate them into a unified secret management system so that we can stay secure. So what are some of these awkward workarounds? Just a disclaimer, I'm not actually recommending any of these. The first one is we could just bake the secret into the AMI. But really, this requires a unique AMI per security boundary. And so as a result, it requires a different AMI between QA and prod. I'm assuming you do want different secrets between QA and prod, right? It also makes rotating the secret hard. I'm being told I need to change my mic, so 1 second. Right. All right, much better. Sorry about that, technical difficulties. So as I was saying, if you bake your secret into the AMI, rotating it becomes much harder. You need some sort of AMI pipeline. And I'm assuming you are rotating your secrets, right? That's why you're all using Vault. And then what you end up with is you share secrets across instances. And when you do this, you lose individual accountability. It becomes very hard to track who leaks your secrets when they get leaked. Not if, but when, because this type of compromise is just inevitable. So second awkward workaround is we could store the secret in S3. Now, back in the days when we first started working with this is before KMS and before VPC endpoints. So what that meant is we'd have to store the secrets in plain text in S3. Now, you could say we could encrypt them on the client, but then the question is, where does the client get its decryption key, right? It's basically turtles all the way down. And then we also had to have our instances talk out to the internet. This is before the days of VPC endpoints, as I said, and a huge part of our security model, the threat model that we're worried about, is data exfiltration. So instances talking out to the internet gives us a bit of a heartburn. Now, with the introduction of KMS and VPC endpoints, it's a more palatable solution. We can actually rotate the secrets in situ. We no longer need to bake an entirely new AMI. We can just update it in place in S3. But we still share the secrets across instances. And even worse, this becomes an incredibly difficult problem to reason about. The things that are going to govern access to your secrets if you do this include the IAM policy and role that your EC2 instance is in, the VPC endpoint policy that your EC2 instances are using to talk to S3, the bucket policy on your bucket, the ACL on your S3 bucket, the ACL on your S3 object, your KMS key policy, and your KMS key grants. It's a lot of different things, and each one of those you could easily screw up and potentially have a catastrophic failure of your entire security system. So that is also a very difficult challenge to deal with. The third awkward workaround is we could use some sort of external orchestrator to position the secret. And this comes in two flavors. The first one is we could just use the orchestrator to directly spin up instances and then SSH on when they come up and position the secret. But if we do this, we lose the benefits of AWS managed dynamic scaling. The other flavor is we could set up a listener to AWS Autoscale events, and then when Amazon spins up a new instance, SSH on, position the secret. But this gives us increased startup latency before the service becomes available. Both of these also end up being more complex. The more code you have to write and maintain, more systems you have to keep updated and patched. So it's not really a great solution either. So I've talked a little bit about some of the problems, right? What are the drawbacks of these? But really the question is, what do we actually want? What are some of the security properties of a good system? Note that I'm focusing on security properties here. This also has to be easy to use. And I'm not intending this list to be exhaustive. It's just illustrative of some of the things we want. All right. Does that help a little bit? Cool. All right. So the first thing we want is granular auditability. We want to be able to track down to an individual instance or individual client what any secret, anything is going on in the environment. If you share a token, it makes this much, much harder. The second thing we want is we want no long-lived secrets. The longer a secret lives, the harder it is to know everywhere it goes, the less confidence you have about who possesses it. And you just no longer understand where your secrets are, and then it makes you even more afraid to rotate them, and the problem just compounds itself. And one of Vault's key differentiators is that it's very strongly opinionated that all secrets should be short-lived and temporary, and it sort of forces you to do that with the least concept. The third thing we want is protection from replay attacks. When I talk about a replay attack, what I mean is if I send the same request to Vault twice, am I going to get a valid login authentication token back? TLS provides some great protections here at the transport layer, but we actually want to pull it up a little bit higher into the application level protocol to provide even better protection. The fourth thing we want is credential theft. So an example of this is you never want to send secrets over the wire. It's just asking for them to be compromised. And LDAP is probably the worst offender in this space. For example, if you have a dev vault server and a production vault server both talking to the same LDAP backend, if someone compromises your dev vault server, they could just steal that password and use it to log into the production vault system, or any other system that depends upon the same LDAP backend. So sharing secrets, sending secrets over the wire is always going to be a recipe for disaster. And the fifth thing we want is we want it to be usable from any AWS service. We want it ideally to even be forwards compatible as new services come along. That way we can take advantage of the new services that Amazon offers and be able to securely integrate them into our secret management process. So how do these awkward workarounds that I mentioned earlier stand up to the framework? Well, if we bake it into an AMI, obviously we're not being granular because every instance that gets spun up has the exact same secret. Temporary credentials are possible, but you're going to have to do additional work to make them self-destruct and also have a regular rotation process. You don't get any protection from replay attacks or credential theft because by definition, all of the instances are sending the same data to a Vault server to get a login token. And it only works for EC2. It's not going to work for every other AWS service. Now, if you store it in S3, it is essentially all the same properties, except that rotating it is much easier, and potentially it works for every AWS service. Now, if you use an external orchestrator, there's a lot of knobs you can tweak to try and gain some of these properties. You can be very granular. For every instance that comes up, your orchestrator could just get a wrapped Vault token from Vault and positioned onto the node, and so you get lots of granularity. You get the temporariness for free because Vault provides that with token TTLs. You get replay protection and theft protection because your instances are never actually talking directly to the Vault server. But again, it only works for EC2 instances, doesn't work for other AWS services. So enter Lyft's Confidant. I'm only going to talk very briefly about this because this is a talk about Vault, not Lyft, and not Confidant. But about the time we were starting to run into this, Lyft released Confidant, which is also a player in the same space. And in fact, Confidant uses KMS in a pretty clever way that actually checks all of the boxes that we want. So why not just abandon Vault for Confidant? Well, a few reasons. First of all, it only runs on AWS, so we lose flexibility. We're an enterprise with an on-premise data center footprint still, and so we can't just ignore an important part that's still running the business. Secondly, it requires clients to talk directly to the KMS, which as of today is still only available over the public internet, and we get the same heartburn I mentioned earlier of having compute resources talk directly to the public internet. The third thing is, and in my opinion, this is the biggest deal, Confidant does not have Vault opinionation that all secrets should be temporary and expiring. It's a secret sharing solution. It's not a secret management solution. So let's talk a little bit about something called the EC2 Instance Identity Document. Amazon provides this to all EC2 instances. If you look at their docs, this is an example of what it looks like. And if you look at it, you see it contains metadata about an EC2 instance. What you don't see here is that it's also cryptographically signed by AWS. And it's only available via the instance metadata service, so you can only get it from being on the instance itself. Could we use this to authenticate to Vault? Well, what would this naive approach look like? Let's just take a naive approach. The workflow would basically be the client's going to retrieve a signed instance identity document from the metadata service. Client sends the signed document to Vault. Vault verifies the signature. And then a Vault role would map an instance to policies using attributes about the instance. Well, how would this naive approach fit in our framework? So this is sort of where we stood before with the awkward workarounds. And if we add in the naive identity document method, we get good granularity because it is good for every single EC2 instance. It's not temporary, though, because the instance identity document doesn't really change as long as an instance is running. You also don't get replay protection or theft protection because any instance that any other process could potentially just also retrieve it and send it to Vault and impersonate that instance. Additionally, it doesn't work for every other AWS service. So there's a few things that the Vault engineering team worked on to improve this naive approach. Because as I said before, it has a number of drawbacks. I'm not going to talk into detail about this because I'm assuming you all want to get to the closing happy hour tonight. But some of these knobs include things like role tags. So a role tag is a tag you can apply on an EC2 instance that makes a role strictly less permissive. Client nonces is something that clients use at first authentication to prevent somebody else from reusing that identity document to log into Vault. Disallow reauthentication is a way of just administratively forcing, telling Vault that this instance should never be able to get another login token again. And then allow instance migration is a feature that if the hypervisor sees the instance stops and starts, you can actually relax some of the requirements around reusing the identity document. The fact is, these knobs just add complexity. Every knob you add increases complexity in the system. And the old adage is true. You can't secure what you don't understand. So anyway, so this is original AWS EC2 Authentication Backend. I'd like to thank Seth Vargo for this diagram. I shamelessly borrowed it from the Vault documentation. But the workflow is basically the EC2 instance gets its identity document from the metadata service, sends it to Vault. Vault verifies the signature, goes out to the public EC2 APIs to verify that it's a valid instance and look up other metadata about it. And if it's a valid instance, it compares the metadata about the instance to what's allowed in the role. And if all of that passes, the client gets a Vault token back. So how does this fit in our backend and the framework? And I also want to just preface this discussion by saying that I'm talking about some of the drawbacks of the original AWS EC2 Auth Backend, but please do not hear this as a critique of the Vault engineering team or the work they did. They are very constrained by what was possible in the AWS ecosystem at the time. And I think there's actually a really great and innovative solution given what was possible within AWS, but there are still trade-offs. Every system has trade-offs, right? So it gives you pretty good granularity. You don't really get temporary credentials. You get some replay attack protection and some theft protection. But it doesn't work for any AWS service. It's still EC2 only. So let me just take a bit of a digression into the AWS Authentication Protocol. So AWS Authentication Protocol uses an access key and a secret key, fundamentally. And you can think of these sort of like username and password. The key difference, though, is that the secret key is never actually sent over the wire. What happens is clients create what Amazon calls a canonical request. The clients then sign that canonical request with HMAC SHA-256 with a key derived from the secret key. The signature is then appended into the request, sent to Amazon. Amazon, when it gets the HTTP request, regenerates the canonical request, retrieves the secret key, reassigns the request, and compares the signature. So in addition, the timestamp is included in the signed request, which provides a measure of replay protection. If you're more than 15 minutes off, Amazon just denies the request. Lastly, Amazon has a notion of temporary credentials that self-destruct after a certain period of time, which is also very appealing to us if we don't want long-lived credentials. So can we use this for Vault? Well, the reason it's so appealing is because Amazon's already done the hard work of giving credentials to things running on it. For example, EC2 instances get credentials via instance profiles through the instance metadata service. Lambda functions get credentials through environment variables. ECS task instances get credentials from an ECS-specific metadata service. And the whole point, one of the big points of going to the cloud, beyond just some of the ecological impacts I talked about earlier, is letting the cloud provider do a lot of the hard work for you. And another piece of hard work that Amazon's already done is their authentication protocol is already battle-tested and used across the world. So it meets most of our requirements. It'd be great if we could use it. Unfortunately, the use of HMAC SHA-256 or the secret key means if our Vault were to validate the signature, it would need to know the actual AWS secret key in order to verify the signature. And AWS, for good reason, just won't share it with Vault. Right? I don't want them sharing my secret key with random other processes. That is just a recipe for disaster. So, we're not sort of disaster method yet. Imagine for a second if Amazon had some sort of conceptual who am I method. It would solve this problem. Basically, the workflow would look something like client signs this whoami API request, sends the signed request to Vault. Vault could just forward it on to Amazon. Amazon would validate the signature. And if it's validated, just tell Vault who signed the request. Effectively, this is turning Vault into a man in the middle, but we're doing it intentionally, so it's OK. Furthermore, this would work for any IAM principal type who could call this whoami method. The downside, though, is we sort of need Amazon to actually implement this whoami method before we can use it. Well, turns out that in mid-2016, Amazon finally added it after a couple years of us asking for it in the form of STS get caller identity. Hooray! So what this means is now possible for Vault to just use a native AWS authentication protocol. Again, the naive implementation is you would send what I'm calling a bearer signed get caller identity request to Vault. And then a Vault role would bind an IAM principal ARN to a set of policies. And you can think of this similar to how pre-signed S3 URLs work for those of you who are familiar with that. Sort of a similar concept. The one important thing to note about this is that AWS appears to add no authorization whatsoever around who can call get caller identity. Every IAM principal can call it regardless of the policy. Furthermore, it has no knowledge of MFA. So what this means is you can't add an additional measure of restrictions around who can log into Vault through the IAM policy. It's not a big deal, but it's just something to be aware of so you don't assume that, oh, I have a deny all unless MFA authenticated, so therefore you must be MFA authenticated to log into Vault. I actually tried that. Doesn't work. Sorry. So how does the naive AWS IAM fit into our framework? Well, so this is where we stood before. Now, if we add the naive AWS IAM, it provides us some reasonable granularity. It provides us granularity on the basis of IAM principle, which is actually fairly similar to how AWS handles it. Temporary credentials are possible because Amazon already includes those as a first-class citizen, so we basically get that for free. We also get replay protection for free. We get some credential theft protection. And so, for example, the secret key is never sent over the wire. So a compromised dev vault server could never actually be used to authenticate itself to AWS for anything other than this get caller identity request. However, if you have the same IAM principle ARN bound to roles in both a dev vault server and a prod vault server, then a compromised dev vault server could actually then re-authenticate to the production vault server and get production vault credentials. It makes us a little nervous. We can fix it. And then it would work for any AWS service to which you have IAM credentials. So how do we protect against this credential theft? Amazon, as I said, gives us a lot for free, but we can do better. The solution is actually quite simple. Add a header. The AWS Auth Protocol provides a mechanism to include arbitrary request headers within this canonical request that gets signed. And in particular, Vault knows about a special header. This header is x vault AWS IAM server ID. And this is also not case sensitive, by the way. And what you can do is per mount of the AWS Auth Backend, you specify a required value. And my recommendation would be specify a unique required value per security boundary. For example, it could be the Vault cluster address that clients use to talk to it. Then if you configure that value, Vault does a few things. It validates that the header value that's included in the request is what was configured administratively on the mount. And then it also validates that the header is actually inside of the signed headers in the canonical request that gets sent to Amazon. And it just forwards it to Amazon. Amazon validates the signature for us, making sure that nobody's tampering with it. And we get it for free. So you should configure it. Now, the question is, how do we send the signed request to Vault? I sort of have been glossing over it. And it is the most complex part of this whole workflow. Basically, Vault needs to recreate the original signed request so that it can forward it onto AWS. And in order to do that, it needs 4 pieces of information, all of which are in the canonical request. The first is the HTTP method, and right now, post is the only one that Vault supports. You need the HTTP request URI, which Vault expects to be base64 encoded. You need the HTTP request headers, which is a base64 encoded JSON serialization. And then you also need the HTTP request body, again, base64 encoded. So what do these look like? Well, IAM HTTP request method is just post. Pretty simple. It's the only thing we support, so you kind of have to put it there. If we look at the IAM request URL, it's this base64 encoded string, which is really just sts.amazonaws.com, which, as a side note, Amazon just canonicalizes this to a slash. You can do either. It doesn't matter. IAM request body is this bit of base64, which in reality is just the encoding of action equals get caller identity in versions 2011-06-15. So request methods post, these are the post parameters, nothing too surprising here. And the last one is IAM request headers. And that's a bit of an intimidating piece of base64. I will admit that. If you base64 decode and pretty print the JSON, this is what you get. There's a few things to sort of note in this. The first is you see the xvault AWS IAM server ID header. So that's the header that we configure and tell Vault. And if you look in this authorization header, about midway through the second line, you see where it says signed headers is host, xamz date, and xvault AWS IAM server ID. So that's how Vault verifies that it's inside of the signed request that goes to Amazon. And you also see the xamz date. That's how Amazon provides replay attack protection. But this whole authorization string probably still looks pretty magical to most of you. And so really the question is, how do we generate it? And if you actually look at the user agent, you'll see a hint as to how I generated this particular request, which was using Protocol. And one last note is, in this request information that's into Vault, in this case, all the values are strings. Vault accepts both strings and arrays of strings, because different languages do different ones by default, and so trying to make it a little more friendly for users. So I said, generating these headers is the hardest part of the login method. Easiest way is the Vault CLI will just do it for you. Vault auth -method is AWS, role is my role. Vault creates creates all the headers for you, sends it to the Vault server. Vault server takes care of all the authentication, and then gives you a token back. Super easy, right? A little bit trickier, but the other recommended way is you can just ask the AWS SDKs to do it for you. You just have to sort of know the right parameters to do. And if you want a going implementation, just look at the Vault source code. It's open source. That's a great part about open source, right? In fact, you could even just import the Vault as a library and use that to do it for you. If you had other languages, ask on the mailing list. I, for example, have posted Python 2 and Python 3 implementations. And I would not recommend trying to actually implement the AWS SIG v4 request protocol yourself, because you're going to spend a few hours on the Amazon documentation. And it's a little opaque. So this is pretty close to the final Am Auth method of AWS. As I said before, we get some granularity. Temporary credentials are possible. Gives us some replay protection. We can now get theft protection with the header if you configure it, and it works for any AWS service. So just comparing the two, AWS EC2 authenticates EC2 instances. And it evolved to allow binding specific to EC2 instances. For example, is the instance in a particular VPC or in a particular subnet? IAM authenticates IAM principles. And so it's ignorant of the bindings that are specific to an EC2 instance, because it could be anything, right? And IAM sort of loses its magic for an EC2 instance not inside of an instance profile. Now, this used to be a bigger deal, but now Amazon lets you dynamically change the instance profile of an instance on the fly, so you don't have to worry about that. However, Vault customers like the flexibility of binding to EC2 specific attributes, and so can we get some of that back? Well, another digression into AWS's STS assume role. The way to think about assume role is sort of a credential transformer. You take one set of credentials, you sign this STS assume role request, you send it to Amazon, and Amazon returns back a different set of temporary credentials. There's two parameters that are germane to this discussion: the target role ARN and the role session name. So target role ARN is the thing that has all the policies and permissions that you get from assuming it, and it's sort of governed by the way you just think of normal AWS IAM permissions. But then there's this role session name parameter, which is chosen arbitrarily by the client. Now, importantly, both of these things, both the role name and the role session name, are visible to the responsive get caller identity. And furthermore, the way to think about an EC2 instance in an instance profile is if EC2 itself calls assume role on your behalf and then presents the return credentials to the EC2 instance, and it chooses the instance ID as the role session name. So what this means is that EC2 instances and an instance profile have a recognizable pattern. So Vault has a feature I call inferencing. If you turn it on, it tells Vault to infer that the authenticated principal is also some other type of entity. Right now, the only type supported is EC2 instance. And if you configure it on a role, Vault does a couple of things. It ensures the role session name is a verifiable EC2 instance ID. And if it does that, it actually allows most of the binding specific to an EC2 instance, whether it's in a particular VPC or subnet. But it does require telling Vault how to validate the instance. And really, the additional thing it needs to know is what region it's in. IAM is a global service. EC2 is region specific. So you have to tell Vault what region to look up that instance ID. And one final note is you must be careful about IAM update assume role policy. And the reason is because I said earlier, role session name is chosen arbitrarily by whoever's calling assume role. So if I could call update assume role policy, I could let myself assume the role that the EC2 instance is in. I could just give myself permission to do that. Then I could just call assume role, pass in the instance ID as the role session name, and masquerade as your EC2 instance to Vault. Now, it's not dire, because if someone has updated assume role policy, it's a pretty privileged person in your account already. but it's just an important part to know about the security model because Vault's all about being transparent about the security trade-offs that are available in Vault. And if you're uncomfortable with this, then you just don't need, you can either go back to the EC2 Auth method or don't use inferencing. The last thing I want to talk about is AWS IAM internal IDs. So every IAM principal, whether that's a user, a group, or a role, gets a unique internal ID that generally isn't exposed to the console. And if you delete and recreate a principal with the same name, you get a new ID. So if I create an IAM user named Joel, and I delete it, and then I recreate a new user named Joel, that's going to have a different internal ID. And by default, Vault uses this internal ID. So when you create a role, or when you update bound IAM principal ARN, Vault looks up that unique ID. And then at client login time to Vault, Vault sees the unique ID and the get caller identity response and compares that with the stored value. So if I configure a bound IAM principal ARN of the Joel IAM user, delete it, recreate it, get new credentials, try and log into Vault, it'll fail because Vault sees that internal ID has changed. And again, this is just the exact same way that AWS operates internally. If you pass in an IAM ARN, behind the scenes, it'll just translate that to the internal ID. And then if you delete that entity and recreate it, you'll see the internal ID back in your policies. So this is really naturally aligned to the way AWS manages a lot of their IAM permissions. However, wildcard binds don't and can't use internal ID. So a wildcard bind is where you specify a glob at the end of a bound IAM principal ARN, and those will just do a plain textual match because A, it's not possible to do anything else, and B, that's sort of what AWS does as well. So this is the final Am Auth method, pretty much as it is today in Vault. Do you get granularity? I think you get pretty good granularity. You get the granularity based on IAM principal ARN, and also based on EC2 instances if you want it. Temporary credentials are possible because they're first-class citizens. You get pretty good replay protection because Amazon gives you that for free. You can configure the header value to get theft protection, and it works for any AWS service. And more importantly, I think it's going to be future-proof. So for any future AWS services that come up where you get compute resources, Amazon's probably going to provide them with credentials, and you can just use that to authenticate to Vault. We don't have to worry about trying a new login method every time Amazon launches a new service. And I think it gives customers a lot of flexibility to meet their security goals in order to easily log into Vault and authenticate to Vault and maintain a holistic security environment. So if anyone has questions, hit up the Vault mailing list. I'm pretty active on the Vault mailing list. You can also email me directly. I'd love to collaborate if people want to collaborate. And lastly, just a few acknowledgements. I'd like to thank Dan Peoples, who's co-pumpkin on GitHub. He's a coworker of mine at Bridgewater and really has just been an invaluable thought partner as I worked through this. He reviewed all of the code before they ever saw the light of day of a public pull request. Just in general, all around, super smart guy and really helpful. I'd like to thank Jeff Mitchell and Vishal Nayak of HashiCorp for all of their patience as we worked through this pull request. In fact, it was actually 2 pull requests. And at the time they got merged, I was responsible for 2 of the top 5 most common pull requests in the Vault repository. So tremendous thanks to them for all of their patience and help in how to make this great and a really great solution for all the customers. I'd like to thank our AWS Enterprise support team as well for help on that. There was some assumptions we wanted to make about get caller identity that weren't necessarily included in the documentation. And you don't want to have the core of your security system depend upon some assumptions in a third-party product. That's not a good idea. So they were super helpful and responsive in clarifying how the assumptions we were making worked and allowed us to build a really supportable, stable product. I'd also like to thank you all, the community, for just being a great community. It's a really fun group to be a part of. And lastly, I'd like to thank my pet cat, Mio. When I first started writing the code, she wanted to help me write the code. So here she is, literally helping me write this code. So if there's any bugs, blame them on her. Thank you all.